All right, good afternoon, everyone. Welcome. This is Control with Wireless Roundtable. I'm your moderator, Neil Peterson. I'm a Delta V marketing director. I have responsibility for hardware, Delta V SIS, security, networking, and wireless. And so there's my connection. So I'm going to moderate today. This is a roundtable, so we want some audience participation, right? Emerson Exchange, we want to hear from you as well. The way we're structuring this is we're doing it in short little presentation vignettes, okay, where we will present a topic and then open it up to questions, and I'm going to grab that microphone and run around like a crazy person to hold it so you can ask questions and we can start a discussion. So we're going to do a short presentation, short period of question and answer, and then we'll move on to the next period of presentation. We've got 4 different topics we're going to talk about. I'll control the time, and I may have to cut you off if we don't answer your question. Of course, afterwards, out in the hall or at the exhibit hall tonight, you can feel free to find any one of these fine persons and ask them your question. So with that, I'll get started with the presentation. So first, let me introduce our distinguished guests. We have Terry Blevins, Principal Technologist from Emerson Process Management. Terry led the development of Delta V advanced control products. He co-authored the book Wireless Control Foundation, from which this roundtable is based, and the ISA best-selling books Advanced Control Foundation and Control Loop Foundation. Terry received his Master of Science in Electrical Engineering from Purdue University. The one thing we have in common. I don't have a master. And in 1973, he's a member of Control Magazine's Process Automation Hall of Fame, something I'll never achieve, and an ISA fellow. Presently, Terry is a principal technologist in the applied research team at Emerson Process Management. Awesome. Bailey Roach is a PhD candidate from the Process Science and Technology Center at the University of Texas at Austin. Bailey is currently pursuing she's a Virginia Tech graduate. She held an entry-level engineering position with the ExxonMobil prior to entering graduate school. Her PhD studies involved building a pilot-scale dividing wall distillation column, which will be used to develop the basic simulation design control methodologies. The research program combines industrial experience and academic research expertise to develop a novel separations technology which will address current and future process requirements. Curtis Jensen is a manager of Fisher Field Instrumentation at Emerson Process Management. He has over 30 years experience including field service, control systems, RTUs, and SCADA systems, telecommunications, wireless technologies, and field instrumentation. His current responsibilities include managing transducer, controller, level, and other related control products and accessories, all to do with wireless. Wired and wireless? You do wires?
A lot of pneumatic stuff is wireless.
Wires are so 20th century. And then finally, we have Eric. Oh, now I've been pronouncing it wrong so long.
Right.
Citrinovich.
There you go.
Oh. Eric Citrinovich, RTU Product Manager, Emerson Process Management. He is the RTU Product Manager with Emerson's Remote Automation Solutions Business Unit. He has over 20 years marketing and product development experience in manufacturing, power generation, and oil and gas industries. He has a BS in chemical engineering and an MBA in industrial marketing. So, distinguished panel, a lot of experience, a lot of education, know what they're talking about. And so this is the agenda. So these are the different topics we're going to be talking about. Terry's going to kick us off with wireless control guideline, and then Bailey's going to talk about the dividing wall column control using wireless transmitters, and then we'll move into control using wireless valves. And then finally, how wireless control using a ROC 800. So a lot of different topics for you to discuss. And with that, we'll kick off to Terry.
Yeah, thank you, Neil. As we introduce new technologies, there's always this question of, well, what are the guidelines on applying this? Like, am I going to get in trouble if I apply this? How do I apply it in the best way? So I thought it'd be interesting maybe to talk a little bit about guidelines, not that we know everything, but reflecting about 10 years of work in this area, the guidelines that we would propose that you maybe follow as you look at wireless control. As you look at this area, it's one that's sort of surprising. The rate at which wireless has been adopted is quite amazing compared to other things that have been introduced in the process industry. Essentially, that market has gone from about 0 up to $300 million per year in a 6-year period of time. There are very few technologies that have taken off that fast in the industry. Part of that success is due to the fact that wireless and the way the gateway works makes it fairly easy to install, and it's fairly forgiving in terms of the installation. If you have a straight line of sight, you can go quite a distance, but you don't have to have straight line of sight. One of the things that you'll be hearing from Bailey about what's been done at UT, but you look at the installation there on wireless, and the gateway is in no way straight line of sight to any of the transmitters. There's quite a distance and obstacles in between. One of the nice things is with wireless you have reflection of the actual transmission that's going on, and through those reflections you really can get to points that aren't in the straight line of sight. When you look at wireless and you start setting up your wireless device, there are some choices in terms of communication. And if you're looking at communication and you're thinking about using that device in closed-loop control, then the two primary candidates for communication are something called the continuous communication. That means that the device wakes up periodically, senses the measurement, then communicates that, and then goes back to sleep. And it periodically then wakes up. The period that it wakes up, you get to specify. So that's your configuration parameter. The other technique that is often used in control is window. It's similar to continuous in that the device periodically wakes up, but then at that point in time it says, has my measurement changed by more than a certain resolution? And if it hasn't, it doesn't communicate it unless it's been a certain period of time since the last communication. So that's called window. It always uses less power than if you're doing continuous. But one of the considerations is with window, you now have aperiodic communication of your measurement. And so your control has to be structured to be able to handle that. Most of the devices out there today are battery powered. In terms of thinking about battery powered devices, then this period of communication has a direct impact upon the length of time you can operate with that battery before you need to replace it. An awful lot of people that I've talked to have said they really want the battery to last 5 to 7 years. So if you look at this, you'll see that you really need to be setting up communication for about an 8-second periodic update if you're trying to achieve this 5 to 7 year battery life. Now, an 8-second update is quite a bit slower than what you have in your control system today. If you look at it, the recommendation is that over your control response, process response time, that is the time from you making a change to getting to 63% of the change is the process response time. Recommendation is that you at least execute 4 times in control over that time frame. And in most of your DCS systems today, to minimize the delay between the measurement being taken and being used, we highly oversample the inputs. So like in delta V, your analog input is being updated by your heart transmitter over 20 hertz, so about every 50 milliseconds or a little less. In delta V, the I/O on that is updated about every 50 milliseconds. So when the actual control executes, there's very little delay introduced by I/O access. But if you said, well, now I want to set up my wireless to do the same thing, you burn out your battery in a few days here just due to the power that would be required. So if you have a slower processor application, though, where this 8-second update is giving you 4 updates over your process response time, then you see just using a regular PID, it doesn't do such a bad job. Okay, so let's say you had a process that was, 30 some odd seconds response time, then an 8-second update period. you could use regular PID and get away with it. But if you said, well, I really have processes like liquid flow, liquid gas, other things that are much faster, and you take the case where maybe they're twice, 2 times slower than the process response time in terms of your update. So let's say you had a liquid flow loop that's a 1 second response time and you're communicating it every 2 seconds. Then if you have it properly tuned, you look like this. Not so good. Okay, so what do you do? Well, what I tell people is that up until now, the DCS has been designed and your I/O access with wires been designed where we could very successfully mimic analog control. So up to this point in time, the technology has been just designed to mimic analog control. When we get into wireless, you really need to talk about a different control structure. And fortunately, there is one. By looking at the PID and looking at the way the reset is calculated, the derivative is calculated, you can restructure the PID to give you something called PID Plus capability. That means that your reset contribution and your derivative are only updated when you get a new communication. Your proportional continues to operate all the time. Now, when you deal with this new technique, the actual PID needs to execute much faster than the actual communication rate. So if you had an 8-second update, you may be executing this every half a second, say. And the reason for doing that is to minimize the amount of delay you introduce into control. So as soon as the new measurement is in, you're using it. And so that's an important aspect of applying this PID Plus. But if you apply PID Plus, I think you'll find it gives you very comparable performance to what you get with a wired system. In this case, we're talking about using windowed communication, non-periodic update with a 1% resolution, really coarse update, 10-second refresh time, and yet you notice on a set point change, response looks very close to what you get with a wired. So we're comparing a wired transmitter with PID to wireless with PID Plus here. You notice though on an unmeasured disturbance, it doesn't do quite as well in terms of recovery. But you notice every time you get a new measurement update, you're right where the valve would have been if you had had a wired installation with PID. Okay, so it does a good job. Not quite as well as you would get with a wired installation if you compare like integral absolute error. But the important thing here is that in this example here, we only had 25 wireless measurement updates. With a wired installation, we had over 600 updates. So it shows that you can do an awful lot with fewer communications if you structure the PID in this manner. A concern oftentimes is loss of communication. So if you lose communication, the PID Plus really outperforms the PID because the PID, under the condition of a loss measurement, just continues to ramp the output with the reset action. With PID Plus, since it only updates reset contribution when you get a new measurement, it only updates or changes with the proportional error in terms of the output. And so it provides really superior performance on loss of communication. With PID Plus, it's a standard feature of Delta V. So if you have Delta V version 11, version 12, then it's just the frizzy PID option. You select PID Plus, and now suddenly you have that capability. So it's that easy in terms of turning on that capability. But we wanted people to be able to use this irregardless of what control system they had. And that's really in best interest of our measurement division. They'd like to sell to anyone, no matter what system they have. So the patents that we have, and we have 3 patents on the technology, were given to Fieldcom last year. That's the organization that really represents Foundation Fieldbus, HART, Wireless HART. So what that means is that as an end user, anyone can apply PID Plus without violating our patent as long as you're using Wireless HART for the transmitters, the field devices. So after this announcement, I was approached by one of our major oil companies in upstream oil and gas. And they wanted to try this because they saw a lot of value in wireless control for upstream applications. The problem was in their research facility in Houston, their flow lab had LabVIEW as the control system. So I said, well, we'll work with you and we'll implement that in LabVIEW. So that's the sub-VI, the sub-virtual instrument that I created. That is PID Plus, 20 lines of code, right, to do PID Plus. So we gave that to them. They installed it in their flow lab. They tried it on a gas flow loop that had a response time of less than 3 seconds. They control that using 8-second update, continuous update. And this is the response from their flow lab. Okay, so that's for set point changes. So this gas flow, they could introduce header disturbances. And so that's what they did to test disturbances. So that's the disturbance response. Not too shoddy there. So as a result of that, they've asked us now to implement PID Plus in the ROC platform, and because they have standardized on ROC. And so Eric will be talking about that in terms of that interest in having that in the ROC platform. Okay, so all this is sort of leading up then to guidelines, background, information, understanding why the guidelines are there. Basically, if you're using a wireless transmitter and you want a 5 to 7 year battery life, you need to stick with about an 8-second update rate. Okay, so that's a recommendation. The module that you're executing, the control end, should be executing much faster than that update rate. You don't want to introduce delay due to the fact that the measurement has come in, but the control isn't going to execute for 3 or 4 seconds, right? You want to take immediate action upon the new measurement as soon as it comes in. So we've sort of flipped the cart here. You know, previously in DCS, we were oversampling on I/O and executing control slower. Here we're executing the control extremely fast because the I/O is coming in at a very slow pace there. I would only recommend you use wireless if you don't have a requirement to respond to disturbances faster than your update rate. So let's say you pick 8 seconds and you tell me, Terry, if I have this disturbance, I need to respond in 4 seconds to it, then I'd say don't use wireless. Not a good candidate, right? But fortunately, most of our applications, the vast majority of them, that doesn't apply to. The fact that you need to instantaneously respond to disturbance oftentimes is not really a requirement for the control. The PID Plus should be used if the process response time is less than 30 seconds. So your liquid flow, liquid pressure, some compositions, some temperatures are that fast. And so for those, I'd really say you need absolutely to be using PID Plus. For slower applications, it's really up to you. You can use PID Plus. You can also use PID. And you may have an older control system, say, that only has PID. And so you say, well, I'll just use PID. It's a slow process. If you do that, be sure and put in logic that is going to take action if you lose communication. Because as shown in that one example there, with regular PID, if you lose communication, that output is just going to wind up to 100% or 0, depending upon your error at the time of loss of communication. So it's absolutely necessary to do that. It's important to think about the response that you want to have in terms of loss of communication. The PID Plus holds last output, other than the fact that if you're changing the set point, the proportional will still continue to reflect that. But if you need something other than hold last position, so let's say you have an integrating process like a level control or header pressure control where it's an integrating process, then you may want something other than hold last value. And if you do, then you need to add in track logic to the PID to detect loss of communication and to position the output to the correct spot. And if the process measurement is noisy, the filtering has to be applied at the transmitter. Otherwise, you get huge aliasing. That is, you see things that really aren't there. So by filtering at the transmitter, you take out the noise before you get it communicated. And actually in that flow lab, and the oil company's flow lab, they weren't using our Coriolis meter, they were using someone else's, but it wasn't due to that instrument, it was due to the way it was installed, but they had a huge noise level in terms of signal. And to take that out, we actually asked them to apply dampening at the transmitter. Okay. So that's just some keys on that. Now, Curtis is going to talk to you about wireless valves. The discrete valve positioner wireless has been around for a while, the 4320. And there have been some good presentations here where people have used that. There's a new thumb coming out that now allows us to adjust the throttling valve. But in terms of applying those from a control perspective, there's some things that we need to take into account if you're thinking about using one of these. And one of them is you again need to execute the control much faster than the communication you expect to the valve, again, to minimize any delay. And you need to, at least with today's technology, look at slower applications where the time to get down to the process doesn't impact you from an operations standpoint. And Curtis will talk about that, but you can have a fairly significant delay going down. And we're doing some things like downstream publishing and time to apply command that will be coming out in the future, but they aren't here right now. So we need to, again, think about the loss of communication to the valve. And the valve is set up where you can actually configure it to say, hold last position or go to a position as part of what it does, rather than you having to tell it to do it. So with that, to open it up, I guess, to questions at this point. Anything? All perfectly clear?
You're all on lunch call, aren't you?
Yes, yes. Lately?